Hello and welcome to another measurement and instrumentation class. At the start of this class, we had a small quiz for the in-person students. I'm going to post a quiz for online students as well. I want to go ahead and solve this one, and then we will continue with our class. So the question is that a voltmeter is used to measure the voltage drop across a 5 kilo ohm resistor in series with an ideal 10-volt battery and a 1 kilo ohm resistor. What is the percent error caused by the non-zero resistance of the voltmeter at the following resistance of 500 ohms and 250 kilo ohms? So to start this, first we need to find the true value. True value means the value when the voltmeter is an ideal voltmeter. So if we have a voltmeter connected here, and this voltmeter has an internal resistance, I'm going to call the voltmeter's resistance Rm of infinite, then this would be an ideal voltmeter. In this situation, there would be no current passing through this voltmeter. Therefore, all the current would be passing through the load resistance. Now, to find this, we can simply use a voltage divider. So using a voltage divider, V of R1 is going to be equal to R1 over R1 plus R2 times Vs, which is our source voltage. So it's going to be 5K over 1K plus 5K, which gives us 6K times 10. So it's going to be 50 divided by 6, gives us 8.33 volts. Now, this is our true value. An ideal voltmeter, if it was connected to this, we would get a value of 8.33. If the voltmeter is able to calculate anything or measure anything close to this, we have a high accuracy. And if it deviates from this, imagine if we measure something at 4.15, it means it's 50%. It has 50% error. If it's 8.33, then it's like 100% and doesn't have any error. So 0% error. So let's keep this in mind, the true value, the benchmark that we are looking for. I'm going to write it's going to be 8.33 volts. This is for VR1. Now, for scenario A, our voltmeter is not ideal. It has an internal resistance of 500 ohms. And this is going to be our galvanometer or voltmeter. And now I want to find the the voltage that this voltmeter is measuring and therefore measure its current as well and measure its error as well. Now to do this, we have now, instead of having one resistor in the load, we have two resistors in the load which are in parallel. So these two now are in parallel. And I have to find the equivalent resistance. And the equivalent resistance for this, I'm going to call it Req. So Req would be 500 because they are in parallel times 5K or 5,000 over 500 plus 5,000. And this gives us something which is closer to the smaller resistance. It's going to be 454.54 ohms. Okay. Now, if I want to find the voltage of this, there are multiple ways, by the way, to solve this. One way to solve this, I can find the current. I can use current divider and find the voltage across point AB. Another easier way to do it is just by simply using another voltage divider. And again, if I have the resistance here, I'm going to replace it again with the 454.5. So the resistance voltage or the load voltage here would be 454.54 divided by 454.54 plus the 1K that we have here, or 1,000 ohms, times 10 volts. And this gives us 3.125. Again, another way to do it, you can simply find the current. It's easy. I would be V over R. And what is our V? Total V is 10 volts. And the R that we have, it's going to be 454.54 plus 1,000. And finally, the voltage at AB is going to be that current times the voltage, if we want to find that. So we can use a current divider to find each resistor's current as well. But the easier way is just to use this. Now, the percentage of error is going to be equal to 3.125 minus 8.33 volts over 8.33 times 100 to give us the percentage of error, gives us a 62.5% error. And it's negative, meaning it shows 62.5% less than the actual value. Now for part B, and this was part A, for part B, we can do the same thing, but instead of having the 500 ohm, we have 250 kilo ohm. So our EQ for part B is going to be equal to 5,000 in parallel with 250,000, which is 250K, which gives us 5,000 times 250, so 5 times 250 over 5 plus 250 gives us a REQ of 4,901.96 ohms. My calculation. If your calculation is a little different, it's okay, as long as it's close to this. Now, if I want to find the voltage of the between point A and B, let me call it VAB. We would have 4,901. Let's round it up to 4,902 actually. Over 4,902 plus 1,000 gives us 8.3 volts. Now the percentage of error for part B is going to be equal to 8.3 minus 8.33 divided by 8.33 times 100% to make it percentage, which is going to be 0.033%. It's negative. So the error for the second one is going to be 0.33%, 0.33%, and for the first one, it's going to be 62.5%. Obviously, bigger the resistance is, you're going to have less error. In an ideal situation, you want this resistor to be at least 100 times or more, which is close to infinite. So you're going to have the minimal error. But sometimes if you have like 10, 20 times, it's going to work okay as well. So for part B, error is going to be 30.33%, less than 1%. And for part A, it's going to be equal to 62.5%. Who got this right? Any of you? Did you get it? Okay. Now, again, another way you can do it is you can measure, calculate the currents, and I will show you if you calculate the currents, you're going to get the same results. It's going to be the same. So there's multiple ways to solve this. Now, in the previous class, we started with voltmeters, ammeters, and ohm meters, and the effect of the resistance, the series and parallel resistance on the measurements of the voltmeters and ammeters. And we started with RC circuits, the charging and discharging of a capacitor, how that works. And what happens to a capacitor when it's fully charged, what happens to it when it's discharged. We also calculated, I also gave you the equations for that. Again, you don't need to know the proof for it. For a charging capacitor and discharging capacitor, and the time constant tau, which is RC, which is a very important measure. Today, we're going to solve some examples. And also, if we have time, after that, we're going to start with RMS values and what is a root mean square value and an effective value. Yes. 40. Yes, thank you. Yes.
So at discharge or charging, with discharging you do have current right at that point when it starts to discharge.
Yes, the moment that you. Yes, exactly. And both of them start at maximum current. Both at charge and discharge, the current graph looks exactly the same, but the voltage and charge graph look opposite. Before the moment that you press the switch, both of them have a current of 0. But the moment that you close the switch, charging or discharging, both of them are the same. The current is maximum. And then while the capacitor is discharging, that current falls as well. Yes. Let me put it this way. An easier way is like this. Imagine you want to, put air into your car tire or a ball, and imagine if it's completely deflated and you're using this hand pump to. When it's completely deflated, what is the maximum air that I could put? Is it easier to just pump air into it or no? It's going to be very easy to do it. So you're going to have maximum current or air pressure going in. Okay? And when it's getting full, you have more pressure and it's going to be much more difficult to pump. So each time that you pump, you're going to get less and less air getting into it. Okay? Same thing. And when the tire or the ball is fully inflated, the moment that you open the valve, you have maximum pressure coming out, maximum air current, I could say, water if you have a reservoir. But when it's completely deflated, that stream becomes minimal or it fades out. So again, the discharge current for both of them, for charge and discharge, you can see this is for discharge, and for charge, it was exactly the same. The current starts from maximum the moment you close the switch, and it drops to 0. That's the reason you have these sparks when you usually, turn on. Yes, exactly. Yes, thank you for that point. So 5 tau at 5 tau it subside means that it reaches its maximum. And after that, if it's discharging or charging, it's close to 0. When it's charging, it's not going down to 0 because capacitors that we have, they don't have an ideal dielectric between the conductors. So there's going to be a little bit of leakage between the positive and negative. Okay. These capacitors, and we call these NME transistors, NAND, or we use NOT transistors, are also used in flash drives. So there's not just only used in power systems. They are used in power systems, control systems, electronics. If you have a flash drive, they work on the principles of charges and discharges. That's the reason if you leave a flash drive, you just put it on a drawer for a very long time, it's going to discharge very slowly and it's going to lose all the data on it. So if you have an SSD, it's better to plug it in every year or 2 year or 3 year. So if you leave it for a couple of years, it's going to completely discharge. So they have like, I want to simplify. It's not that simple. You have these capacitors that if the capacitor is fully charged, it's a logic of 1. If it's discharged, for example, it's a logic of 0. But the problem with these capacitors is actually a transistor there, is it slowly discharges over time. Why? Because we don't have an ideal capacitor. The problem with the capacitor actually is that it's very good at charging and discharging, charges and discharges pretty fast. In 5 tau, it's like in microseconds, or even very large capacitors in seconds. But the problem is they don't hold the charge for a long time. That's the reason we can't use it for power storage. But if we want to use it for something that balances power, like in a grid or a racing car that you want to, push on the brakes and use that energy again in the next turn, capacitors, what we call supercapacitors, are very good because they're very good at fast charge and fast discharge. Battery cannot do that. You're going to destroy the battery if you do a fast charge. Batteries are very good for long term. Capacitors are very good on short term. Okay, so these 5 tau maximum that they could reach maybe a few seconds or so, and then it's going to be fully charged or fully discharged. Is it clear? Yes? Okay. Now, for when it's charging, the voltage is opposite. So when it's charging, initial voltage was 0, and it goes to the max. When it's discharging, the initial voltage is maximum because it's fully charged at the beginning, and then it drops down to 0. And this is both the charging and the voltage, because as you know, the equation for the relation between the voltage and the charge in a capacitor, you remember what was it? Q is equal to what? CB. So they have a direct linear relation. V goes up, Q goes up, Q comes down, V comes down. And C is constant here, okay? So this graph is the same as the voltage graph as well. You just multiply it by C. Now, let's go back to an example. For the following circuit, the capacitor is 8 microfarads. By the way, capacitors, especially in electronics, are in range of micro, nano, picofarads. A 1 farad capacitor would be the size of this room. So it's, unless you put like multiple small ones in parallel to make a larger capacitor, but a 1 farad capacitor is a huge capacitor. So usually they are in the range of micro, nano, picofarads. Do you know what micro is? Do you remember what micro is? 6. What is nano? And pico? And usually we don't go lower than pico. And in a capacitor, when you look at a capacitor in a lab, we have different types of capacitors. The cylinder ones, which have a polarity, and there are these small ones which look like a bean, and they have a number on it, like 104. 104, it means it's 10 times 10 to the power of 4 picofarad. So it's going to be 10,000 nanofarad or 10,000 picofarad or 10 nanofarad, something like that. So let's go back to the question. For the circuit shown, C is 8 microfarad and delta V is 30 volts. Initially, the capacitor is uncharged. The switch S is then closed and the capacitor begins to charge. You can read faster than I can. We want to determine the charge on the capacitor at T equal to 0.693 of the time constant, which is RC. This is tau. After the switch is closed, we want to determine the current through the capacitor and voltage across the capacitor terminals at that time. The first question is this: is this a charging capacitor or a discharging capacitor? Okay, so the first thing that you have to determine is you need to know if this is charging or discharging. Why? Because the charging equations and the discharging equations are different. The charging, when it's charging, initial current is 0. When it's discharging, the initial current may be like 5, 10 amps, something like that. So that's very important. So the highlighted text tells us this is a charging capacitor problem. Now for the charging capacitor problem, and by the way, in the exam I will give you this table. You don't need to memorize it. All the equations will be provided. So if we go for the charging capacitor, these are the equations for a charging capacitor. First thing we want to do, we want to find QT, or the charge, at T equal to 0.693 of RC. So QT is equal to the final charge, Q final, 1 minus E in the power of negative T over RC. T is 0.693 of RC, so we can cancel these RCs. Delta V was 30 volts, and C was 8 microfarads, so 8 times 10 to the power of negative 6. And when we calculate that, E in the power of negative 6.93 is going to be 0.5. And 8 times 10 to the power of negative 6 times 30 gives us 240 times 10 to the power of negative 6 times, this is going to be 0.5, or half, gives us 120 microcoulomb, which is the unit for charge as microcoulomb. Now we found the charge. Next, we need to find the current. Do you remember what the current equation is? I is equal to dq over dt. If you go here, you can find the current as well. This is the final equation for the current. So if we go back, the equation for the current, we can take the derivative out of the equation for the charge. But first thing is that we can't use delta V equal to IR. Why can't we use delta V equal to IR for this? We can't find I equal to delta V over R. Let me put it this way. We want to find current, but we can't use delta V over R. Why? Because we have two unknowns. We don't know R and we don't know I. We just have delta V. But if in the exam you had R, you can easily find it using delta V over R, okay, at each point of time. Now, since we don't have that, and we don't know what I is, so IT is going to be D over dt, Q final 1 minus E in the power of negative T over RC. So finally, IT would be negative Q final E negative T over RC times 1 over negative RC. And if we simplify that, we get to this equation. It's going to be CV over RC. And C's cancel each other, the capacitors. And we get to delta V over R, E in the power of negative T over RC. The only thing that we need to do is to replace the variables with their numbers. We have T of 0.693 RC, so we will replace that. Delta V was 30 volts, and R was unknown. Since delta V is known but R is unknown, we will leave that, and we can write it like this. Delta V over R is RI. So I at 0.693 of RC is going to be half of I naught. If we add R, we can provide a numerical value for that. Or we can leave it here as well as half of delta V over R. Now, we want to determine the voltage across the capacitor terminals at the time of T equal to 0.693 RC after the switch is closed. Now, if we want to do that, we just derive an equation for V across the capacitor terminals as a function of time. And for that, Vt is going to be V naught, 1 minus E in the power of negative T or RC. And if we do that, V is going to be 30 times 1 minus E in the power of negative 6.93 RC over RC. In other words, it's going to be 30 times 1 minus half which is going to be equal to 15 volts. Now, why didn't we need to do this? Because we have this R in series with a capacitor, and it's going to have this voltage drop that drops the voltage across the capacitor. Now, what if instead of having T equal to 0.693 RC, we had 5 RC? What would the V be in this situation?
That's 5 tau.
Yes.
C.
So when it's 5 tau, meaning this is completely charged, when it's completely charged, it's going to be an open circuit. When it's an open circuit, there will be no current passing through it. So we're going to have no voltage drop across the resistor. So therefore, this voltage VC would be equal to the source voltage. So VC would be equal to what? Okay. And we learned this previously as well. At 69 percentile of RC, we have half the voltage. When it's 5 tau, it reaches the full voltage. So if we give it enough time, we're going to have the total voltage on the capacitor, or in other words, the capacitor would be fully charged. Okay. Yes.
That time, just going back a little bit to the Penny equations, we don't use that 0.693 to divide over to get, that divided by the 15 volts to get our ratio for voltage. We don't divide the time over.
We already did that 0.693 RC, and it's canceled. We already. Oh, this is VT. This is just showing the T, that the RT is 0.693 of RC. We don't care about how much RC is. So I can write VT here as well. But I wanted to show that this T is 0.693 of RC. Yes, it's the voltage at that time. Perfect, yeah. And if you look here at 0.693, you can see it's about the half of the voltage, depending again on the RC that we have as well. Is there any question about this? Do you have any questions about this part? Okay, now, if we want to find the current, that's easy at that point. At 0.693, we can find the voltage at 0.693, which is 15 divided by R. R is not given here. If we had R, we can easily measure the current at that point as well. And a different way, and by the way, there are multiple ways to calculate this. A different way to calculate it, we have Q, we have C, we can easily find VT using the Q equal to CV equation. So instead of going through that equation, we can go simply, this is much easier. We already have Q, we already have C, we can easily find V as well. And we get the same result as previously, what we had. Okay. The previous one was good if we didn't have C, but since we already have the capacitance, we can easily find the voltage here. Is that clear? Yes? Okay, good. Now, I hope I would add more examples here and some references to those examples. Let's start with VRMS and IRMS. Just give me a second to bring that. And I will share this again. Now, the next chapter that we want to cover is going to be RMS values and powers. Does anyone know what RMS stands for and why do we need RMS values? Yes, root mean square is a term that we use to measure effective voltage in a system. Usually when you're using a voltmeter, digital voltmeter, what you are calculating and measuring is not the magnitude or the amplitude, the maximum amplitude. What you are measuring is the effective voltage or the root mean square voltage. And this root mean square voltage is different in different type of signals. So if you have a sinusoid signal, it's going to be different than a triangle, than a rectangular signal as well. So, sorry, it's a cable disconnection. Okay. Now, let's start with a simple example. Consider the following resistance driven by a sinusoidal source. Now, the current through the resistance here, I is going to be Vm cosine of omega t plus phi v and over R. What is Vm here?
That is the amplitude.
Yes.
The max.
And how do we calculate the, see, can't. So Vm, as mentioned, is the maximum voltage. And there's a difference, by the way, between the maximum voltage and the peak-to-peak voltage. So in a sinusoid voltage, anything between 0 and the positive, it's going to be that positive maximum, that's going to be Vm. And so let me actually just give me a second to bring up something. Just give me 1 second, okay? Sorry. So if I have a sinusoid signal like this, and this is my X and Y, this is going to be Vm. This from the positive down to the negative, this is going to be our V peak to peak. Sometimes we call Vm as V peak as well. Some books I've seen that. So if they say V peak, they mean Vm, between 0 and the maximum. Now, what is omega in that equation? So V is equal to Vm cosine of omega t plus phi. What is omega and what is phi?
Omega is your angular velocity and phi is your phase shift.
Yes, and it's equal to what?
2 pi.
Thank you. And what is F? And how do we calculate frequency on this? So in this particular one, we want to first find the period. Period means the time that it starts and goes back to this initial position. And for example, here, if it's 1 millisecond, t is 1 millisecond, then F would be equal to what? 1 over t. So 1 over 1 milliseconds, or 10 to the power of negative 3, gives us 1000 or 1 kilohertz. Okay? Now, Vm is this voltage here. Imagine if this is, let's say, 3 volts. So the equation becomes like this. 3 cosine of omega, which is 2 pi f, 2 pi times 1000. It's going to be 2000 times pi, for example. And plus phi. What is phi? Perfect. Phi is the phase shift. This one has a phase shift of 0. But imagine if the signal started from here, then you would have the phase shift here, let's say 30 degrees or so. So here we have, for example, for the second one, I have a phase shift of 0. Both of them have the same frequency. Both of them have the same VM, but the second one is a little bit shifted. In most scenarios, we don't care about phase shift, but sometimes phase shift is important. For example, in a 3-phase system, phase shift of 120 degrees differentiates our phases, So now, if I want to find current, let's go back to this. Vm over R cosine of omega t plus phi v. Now, the RMS values, if we want to find the root mean square or the effective values, first thing we need to find the instantaneous power dissipated in the resistance. Power, we know it's equal to Vi, which is going to be Vm cosine of omega t plus phi v. This first term is going to be our voltage. The second term, Vm over R, is going to be our I. Now, if we do that, we get to this equation of P. Our power is going to be half of Vm square over R plus Vm square over 2R. Cosine of 2 omega t plus 2 phi v. Now, in this situation, if we want to find RMS values, again, and by the way, this is for a sinusoid, for a triangle, for a rectangle, any other type of signal is going to be completely different. We're going to find the average power as well. So the average power is equal to the half of real power of Vi conjugate, which gives us half of Vm square over R. Why? Because our load is pure resistive, and a pure resistive load does not have inductive, and it's real. It doesn't have imaginary part. The imaginary part is 0. Now, what we want to do, we have found the average power here. Now we want to consider a DC source driving the resistive load. The average power dissipated in the resistance here is going to be V square over R, and we are mentioning the effective voltage, which is the DC voltage here. Now the RMS value for effective voltage on a DC voltage is going to be V square over R. And if we do it for a sinusoid, we want to determine the effective and an AC, which is the DC, which is equal to the DC voltage that would deliver the same power as AC. So again, the RMS value of an AC is the effective power of that if it was a DC. Does it make sense? Yes. So RMS value on an AC is the effective voltage if we got the same DC. So what we want to do is we want to see how much effective voltage the left one is producing if it was a DC source. Let's put it this way. And we do this, the reason that we calculate average power by equating the average powers for both the AC and DC, and we already did that. And the goal is to determine the effective DC voltage that will deliver the same average power as the sinusoidal source. We do this by equating the average powers. So for the AC, the left one was half of Vm square over R. For the DC was V square over R. Now, what is the difference between these two? The half that we have on the left, and for the AC we have Vm, for DC we have V effective. Now, solving for the effective voltage, V effective would be equal to Vm over square root of 2. In other words, V effective square is going to be Vm square over 2, or in other words, it's going to be V effective over Vm over square root of 2. Now, this effective voltage is our RMS voltage as well. So, And it's also known as the root mean square value of the sinusoid voltage. So what is the root mean square value for a sinusoid? It's Vm over square root of 2. What is square root of 2? It's 1.414. 1 over 1.414 gives us 0.707. Okay, so the effective or RMS value is 0.7 volts of Vm, or around 70% of Vm. Now, let's do an example. We have a commercial power at the outlet, which is typically 120 volts. By the way, this is an RMS value. It's not our maximum value. When you're using a digital multimeter, it shows you RMS value. How can I find a Vm? You can simply multiply that RMS value by square root of 2, and therefore it's going to be square root of 2 times 120, and our maximum voltage is going to be 169.7 volts. So the maximum voltage is actually higher than the RMS value, always like that. Another way to measure the maximum voltage is using an oscilloscope. If you use an oscilloscope, you can see the sinusoid, signal, and then you could accurately measure it. But a digital multimeter is not capable of doing that. Most of them, they can only measure the RMS value. Okay, but if you want to see it in real time, you can connect that outlet. Don't do it to your, oscilloscope, before checking, because some oscilloscopes, they can measure voltages that high. They're like, built up to like 30, 40, 50. The ones that we have in the lab, they could measure up to 1,000 volt DC and around 600 volt AC. But most, like the $40, $50 ones, they can't do more than like 50, 60 volts. So be careful before that. Try it. Check and see. Now, it stopped working again. Now the RMS value that we measured so far were for sinusoid. If we have a triangle, for example, sorry, it stopped working. I don't know for what reason. But if we have another type of signal, the equation would be different. So the general equation is going to be square root of 1 over t, the integral over t of Vm squared cosine square of omega t plus phi v dt. This formula calculates the root of the mean of the square of the voltage. And for a sinusoid, the equation would always result to Vm over square root of 2. But if we have a triangle or a sawtooth, it's going to be different. Here, V would be Vm 2t over t minus 1. And therefore, the RMS value would be completely different. It's going to be like this. It's going to be square root of Vm squared 8 over 6 minus Vm squared 12 over 6, and so on. Or in other words, it's going to be equal to Vm over square root of 3. So for a triangle, it's going to be Vm over 3. For a sinusoid, it's going to be Vm over 2. For rectangular, it's going to be completely different. So for each signal, you're going to have a different VRMS. But 99% of the signals that we work in this class are usually power systems or sinusoid. And for that, if we are asking for VRMS is equal to Vm over square root of 2. Okay. But just keep in mind that for different type of signals, you're going to have different root mean square values. Now, for average sinusoidal power or RMS value, the time domain description of the voltage across the general RLC load network and the current into the networks are V equal to Vm cosine of omega t plus phi V, and I is equal to Im cosine of omega t plus phi I. Now this is a passive RLC network, and here we have the average sinusoidal power. If we only have a resistor, we're going to have a real power. If we have a capacitor or an inductor, we also going to have the imaginary part. Now, the average power for a resistor is going to be half of the real part of Vm theta V with the degree of theta V, and Im with the degree of negative theta I. Now, to calculate the average sinusoidal power, we will multiply the RMS value by square root of 2. In other words, Vm over square root of 2 and Im over square root of 2. And then we will multiply them. So instead of having Vm and Im here, we will replace them VRMS with square root of 2 and Im times square root of 2. And if we do that, we get to the P average of VRMS IRMS cosine of theta V minus theta I. I think it's enough. I don't want to go through the power factor and so on. But P average for a resistive load, by the way, is going to be VRMS IRMS cosine of theta V minus theta I. But if we had Vm and Im, it's going to be half of the real part of Vm, Im, theta V, theta I. I think that's it for today's class. Again, I will post the second set of homeworks this weekend, and you're going to have 10 days. And for the online students, I'll post a quiz this weekend as well. Do you have any questions for me? No? Okay. Thank you so much, and I will see you next week.